All right. So hello, everyone, and thank you for joining us for the first ICPC 2022 keynote. My name is Venera Arnaudova, and I will be moderating this session. I'm extremely delighted to introduce our first keynote speaker this year, Shriram Krishnamurthi. Shriram is a full professor of computer science at Brown University. His training is multidisciplinary, so from programming languages to software engineering, formal methods, HCI, security, and networking. He has created several influential systems and written multiple widely used books. He also co-directs the Bootstrap Integrated Computing Outreach Program. He has authored over a dozen papers recognized for honors by program committees. He has received several awards, such as the SIG Plan.
Oh, don't worry about it. It's usual academic stuff. It's fine.
No, actually, they're pretty cool. So let me bear with me for a minute. So it's the SIG Plan Robin Milner Young Researcher Award, the SIGSoft Influential Educator Award, the SIG Plan Software Award, and the Brown's Henry Merritt Riston Fellowship for Distinguished Contribution to Undergraduate Education. And indeed, he has made substantial contribution for what he calls the hardest problem he has worked on, which is computing education research. And he will be sharing some of his insights on this topic during this keynote. So Shriram, without further ado, please take it away.
Thank you so much. And thank you both. You are amazing chairs. You've been so on the ball, and it's been so great communicating with both of you. And we were just talking before the event, and I was saying I'm just so impressed that you're able to pull off organizing an event of this size near the end of the North American US semester and stuff. I'm just, and not to mention COVID and everything else. So thank you for the invitation, and thank you for the organizational work. Really appreciate it. Hello, everybody. My name is Shriram. I do have the Zoom chat visible, so I can see things. I will admit up front, I have a bit of a problem. I think like many South Indians, I tend to speak a little faster than I perhaps should. So if I'm going a little too fast, you need me to slow down or something like that, by all means, jump into the chat and say, hey, Shriram, slow down. Okay, and I will do my best to heed your call. So like Venera said during the introduction, my original training was really in programming languages. But when I was a PhD student, I discovered this other community that was sitting, sort of our cousins, if you will, that were sitting off in software engineering. And I told my advisor, there's this really cool group of people, and I think we should go hang out with them a little bit more. And so for the next several years, I was actually a very active participant in ICFP and FSC and ICSE and things like, ICSE and FSC and ASC and conferences like that. I've stepped up a little bit. I don't publish that much in software engineering anymore, but over the years, I've taken a very long and circuitous route to end up doing a lot of computing education research. And in particular, to me, a critical part of that is emphasizing the R word. Many of us here are educators. I do education as well as a professor, but I'm particularly interested in the research side of it as well, which is viewing computing education with the same rigor and the same formality and precision as we do our other work, like our software engineering work. There are many different lenses through which people come to computing education research. For me, it's been very much, PL and SC, but also some formal methods and HCI work combined with cognitive science principles. That's really how I define my corner of computing education. Okay, so that's a little bit of background. Now, ICPC, of course, is a sort of venerable software engineering venue. Like, you can say ICPC to anybody and they recognize what those letters stand for. They know the conference. It's old and prestigious. I have decided to take some liberties with the name of your conference. So my talk is also organized around ICPC, except for me, my Ps are not programs. They are instead problems, plans, and performance. The C, I will take a little less liberty with. I typically mean comprehension, but sometimes I mean construction and sometimes I mean composition, but really those are all kind of similar and you don't have to worry about that distinction too much. Okay, so the thing is, I am going to give a talk about ICPC, but my Ps are going to be plans, problems, and performance, in particular from a computing education research lens. And one of the things I'm hoping to do is to get more people excited about computing education research as an area. like many of you, as I said, from so that roadmap, I started off as a sort of software engineering PL researcher, and I learned how to morph myself into a computing education researcher. And I'm here to tell you that it can be done successfully, even perhaps, and give you some sense of the kinds of problems that I think about and the kinds of problems that I think you might find interesting and that you certainly have a lot to contribute to. Okay, does that all make sense? That's where we're going. Okay, now there's a very important thing I need to tell you. Okay, during this talk, there will be audience participation. There are going to be questions that I'm going to ask you, and I'm going to expect you to, not just I'm going to ask you, but I'm going to expect you to answer them. Now, there's a trick that I learned from my colleague, Milda Jijitier. So we're going to use Milda's trick here. So the trick is you type in your answer into the Zoom chat, but you do not type enter. Okay, because I don't want everybody to see everybody else's answer. And if somebody gives the answer, you know how it is, right? It's kind of intimidating. Somebody seems to have said the right answer. Nobody else wants to participate. And then you go to sleep. So instead, what you're going to do is you're going to type the answer and keep it ready, but you don't hit enter till I tell you to hit enter. Okay, that's the rule. So I'm going to start with my first audience participation question. Do you understand the rule? Type the answer, but don't hit enter. Okay, now hit enter. Okay, fantastic. Okay, and nobody typed no, right? Okay, very good. And there's always one, you know. Okay, good. You understand the rule, and that's the process we're going to follow today. Okay, good. So 3 PCs. I'm going to start first with problem comprehension. What is this about? So I'm going to start off with a programming exercise. You're all software engineers, so you're not afraid of writing software. So here's a little exercise for you. Okay, I want you to implement a median function. So given a list, if you prefer an array, whichever data structure you prefer, some linear structure, right? List or array. Given a list or an array of numbers, compute its median. That's the task. I'm going to give you a minute to literally go think about it right now. Okay. You don't have to type it into the Zoom chat. Just type it in your head or type it in a buffer. Think about it. Just think about how you're going to implement that. Okay. And imagine you're sort of in an introductory programming class, right? That's the setting we're really in. Obviously, I know all of you know how to implement median. So I'm going to give you about 45 seconds to go think about it. Okay, now here's the thing. That's not actually the audience participation question. The actual audience participation question is this: what can go wrong when a student is given this problem and asked to implement it? Okay. It's not, I'm excluding like obvious things like, you know, the program seg fault or something like that. Okay, maybe at a more semantic level, I want you to tell me what could go wrong. So now I want you to think about that for about 30 seconds and type into the box, but don't hit enter. Okay, any thoughts? Would anyone like to volunteer? If you have ideas, you're welcome to hit enter now. Any ideas about what could go wrong? It's a bit of a tricky problem. Yeah, okay, great. Venera has actually nailed the problem already. Well, oh, yes, Mathieu, thank you. Yes, okay, so let me see. Oh, this is great, great. You're all participating. Oh, confusing median and using mean instead of median. Oh my God. Okay, you people could just give the talk and we'd be done. 0 numbers in a list. Program doesn't handle listing. Okay, fantastic. Good. Okay, so let me give you the list that I had pre-prepared. Okay, so of course, not accounting for the empty input, which one of you mentioned. Not accounting for even length lists. And of course, there's multiple answers, right? You give the left median, the right median, the average of the 2 medians. There's a more tricky one, which is not accounting for unsorted input. So, you know, I do this in my class, and literally about a third of my class, if I give them the list 1, 3, 2, they tell me the median is 3 because they've all been taught that the median is the middle number, right? The stats books, in fact, if you go look at high school stats books, they never say the middle number of the sorted list. They just say the middle number. The sorting part is left unstated, okay? Then there are more semantic kinds of issues, like somebody actually mentioned this, confusing median with mean, confusing median with mode, and so on, right? And I've arranged these in a sort of like least to most semantic problem, right? The first one is called like a sort of boundary condition, but then they get sophisticated, increasingly more sophisticated. Okay, and then yes, there are more philosophical questions like what's a number, et cetera, which are all actually quite interesting, and then what's a floating point number, and so on. And I'm going to skip those for now. Okay, now. So think about this, right? So all of you can guess some of the mistakes that your students can make. And as you imagine, if you give this to your class, you might see every single one of these errors and even more, okay? So what are the consequences of this? So understand what's going wrong here, right? These are not necessarily programming errors. These are problem comprehension errors, right? They misunderstood the problem. And so when a student turns in their solution, all kinds of things, right? They're going to get bad grades, they'll be frustrated, maybe they go stand in the TA lines, the lines get too long, there are too many forum posts, everybody gets annoyed, okay? But there's actually an even more subtle and important, unfortunate consequence, which is the reason you handed out the problem is you had some learning goal in mind, right? And that learning objective is not being met if the student solves the wrong problem. Right? You wanted them to learn some particular thing. Not only do they get bad grade, they don't learn that thing. So the next assignment that tries to build on this, they're not ready for it. Okay. Now, is this a hypothetical thing? Not at all. There's actually a long sequence of papers that shows that students will routinely solve the wrong problem and not even realize it. And there are perfectly good reasons for this. So they might just misunderstand the problem statement. They might have seen something in class last week, and they might they might accidentally retrieve the memory of that. Right? They might take the problem you stated and map it to some other problem that they know. The brain does all these little slippery things, and we can't control for that. So students end up solving the wrong problem and don't even know they've solved the wrong one. Okay, so the point I'm trying to make here is we have a lot of emphasis on program comprehension. I want us to be putting more emphasis also on problem comprehension. Okay. Now, when I talk to academics about this, I usually get a standard solution to this. You ask the student to express the problems in their own words. Okay, I mean, this is like math teachers do this. Everybody does this, right? I have some bad news for you, okay? Which is students don't have their own words. Your beginning student in Intro CS does not have better words than the words you, the expert, already came up with. You ask students to express their own words, and they'll basically repeat the problem statements back, but put synonyms in for some of the words because, like that's the safest thing to do. That doesn't actually demonstrate any understanding. It simply knows that they know some synonyms in the English or whatever language you're teaching in, right? And of course, even if the students were to write these nice big essays, who's going to review all of them? Who's going to check them? Some of us have classes that have, 250 students. Who's going to sit there reading every one of these, like, somewhat distorted descriptions of the problem statement? Okay, so this is a problem we have to deal with, right? I'm going to argue that we can actually get students to use their own words, and we can give them instant feedback in doing so. Okay, so this is the technique we've been studying and implementing for several years now, which is the words we ask students to use are not English or whatever natural language they're using, but instead to write small unit tests. Okay, so here is a unit test. This is the student expressing their understanding of the median function, that if it gets 1, 2, 3, it's supposed to produce 2. Okay, 1, 2, 3, 4, 5, it's supposed to produce 3. Great. And this is a partial statement about the median function. It's not the whole thing, but it's getting there. If a student writes something like 1, 2, 3, 4, they are now forced to make a decision about what the answer is going to be. Is it going to be 2.5? Is it going to be 2? Is it going to be 3? And those represent 3 different semantic decisions. Okay. Or if they're given 1, 3, 2, what do they say? Do they say 2 or do they say 3? This is the student expressing the problem in their own words. Okay. And so what do we do with the statement of expression from the student? Well, I take the perspective that a test suite like this is a classifier. Test suites are binary classifiers, right? You give an implementation to the test suite, and it comes back and says, yes, it's a correct implementation, or no, it's a buggy implementation for the following reason, right? So this is a little unusual, right? We're not putting the program at the center, we're putting the test suite at the center and saying the test suite's job is to sit there passing judgment on programs, which it is, right? So if the test suite is a classifier, we can take this test suite, and if you notice, I've written median of 1, 3, 2 is 3, and we run this against a known correct implementation. And when we do that, it's going to fail, and it's going to come back and say, sorry, that doesn't seem to be right. Now, what happens at that point is a good question, right? So either the student says, oh, I didn't realize it, or they reread the problem statement, or they go post on the help forum, or they go look up their stats textbook, they come to TARs, there's a loop, an outer loop about how that should be dealt with, okay? That I'm not making a decision about how that happens. But the point is, at some point, the student comes back and says, okay, so that needs to be 2, right? And now when they run it against the correct implementation, it passes. But now what we do is we run their implementation. As you can guess exactly what's going to happen now, we're going to run it against a bunch of known buggy implementations that represent all the misconceptions that they have, which are exactly the ones that you yourself typed in the list, in the chat, right? And so these, one is checking correctness, the other is checking the thoroughness of their test suite. So if this sounds familiar, yes, this is exactly mutation testing. But it's not mutation testing against like millions of randomly generated mutants. Rather, it's a kind of semantic mutation testing, right? I don't want my students spending hours and hours trying to like, kill 1,000 mutants. I only want them to demonstrate enough of an understanding of the problem before they go off and start an implementation, right? And this way, they also now have a preliminary test suite they can run against their implementation. So our implementation of this is a system called Exemplar. It's examples and exemplary examples, hence Exemplar. And so this is for our programming language called Pirate. And so you can see here, the student has written check that the median of list 1, 2 is 1.5. They're told that it's valid, and it's also caught one of the buggy implementations, right? This is like maybe the left median. It's eliminated the left median. If you look closely, there's also a little button that says begin implementation. So there's a common file, there's a testing file, and the implementation file. And the implementation file, the moment they click begin implementation, they can start, but it's nudging them to not do it yet, right? It forces them to make that decision to click that button. And it's like, if you haven't gotten far enough with your tests, should you really start the implementation? And it turns out this little nudge actually has an impact on the students' tendency to sort of relax and try more and understand the problem better before they go off and do implementing, right? And another thing we do is we pitch it to students as basically, this is a 24-hour TA available to you. Anytime you have a question, you can formulate it and the TA will give you a definitive answer on whether you've understood the problem correctly or not, right? Now, you might ask, well, what if the student has trouble formulating that example? I would argue that if the student has difficulty even formulating a black box input-output example, they're probably not ready to start writing code yet, right? Because, and we'll talk about this coding and commitment issue, there's a lot that happens when students start writing code. You want to try to defer that coding experience if you can a little bit. So this has a whole bunch of like these different factors that understand human student behavior built in to try to get them to understand the problem before they go off and start implementing. Okay, so I want to draw this back to ICPC, the real ICPC, the program comprehension ICPC, right? So what is the relevance here? What I would say the big relevance here is, before we analyze programs, we really need to understand student conceptions of the problem they're solving. Because sometimes we look at a program and we say, oh, that is a buggy implementation of this problem. In fact, often what's happening is student is writing a correct implementation of a different problem, right? And that is a subtle difference. And you need to know what problem they thought they were solving, because all the things that you think are bugs in the program may not actually be bugs in the program at all. The program is actually perfect. They just solved the wrong problem. And ascribing that to programming error is actually quite dangerous, because that's identifying the wrong root cause of the issue, okay? And I also, when I speak to academic audiences, there's always people who are educators as well, and often want to know, like, well, what's the implication for me outside of research context as an educator? I'd say, well, consider thinking about your pedagogy, right? How much are you doing in your pedagogy for problem comprehension? Given that it's now pretty well documented over the past several years that students have difficulty with problem comprehension, there are good cognitive reasons why they go off and solve the wrong problem. And they need that like metacognitive scaffolding to help them get on the right track. What are you doing to help that? Because in the process of helping them, you're not only improving their learning outcomes, you might also be helping yourself, because you have fewer frustrated students, fewer students standing in line for help, et cetera, okay? Regrade requests, et cetera, okay? All right, does that make sense? Are there any questions or comments? Because that's what I wanted to say about problem comprehension. Okay, if there's anything you want to bring up, you can bring it up now. If not, I can wait for questions till later. And let me move on to the second PC part of my talk, okay? So the second part of my talk is plan comprehension. Okay, so what is this about? Okay, again, there's going to be a programming activity for all of you. I'm going to give you a problem now, and I literally want you to spend about 1.5 minutes trying to write code for this. You can write pseudocode, you can write in whatever language you want, I don't care. Just sit down and think about writing the code for this, okay? I want you to take it somewhat seriously. At least I want you to think about the high-level structure of your code, at the very least, okay? So here is the problem. It's a little lengthy, so I'm going to put up the slide. I'll read it out to you and then give you a chance to work through it. So this is called the rainfall problem, and here's what it is. You're taking a list or an array, whatever language you prefer. It's going to have a collection of rainfall values, which are just numbers. What you want is to produce the average of the non-negative numbers that occur before a sentinel value -999, which is optional. Okay, so that's the problem. I'm now going to stop for 1.5 minutes. Go. Okay, so I'm going to ask you to remember your solution structure. We'll come back to it later. Okay, so now I want to tell you a little bit about the history of this problem. This problem has a pretty infamous history in computing education research. So it was first assigned by Elliott Soloway back in 1984 to a group of students at Yale. Okay, and roughly speaking, the history of this problem is you could describe it as rainfall considered harmful. Okay, so essentially, Soloway assigned, 1986, 116 students, and over 75% of the novices get it wrong. I mean, this is Yale, right? What do you expect? But, you know, we got to make do, maybe at other institutions. So people have tried to replicate this study many, many times. So this was studied in 1994, and in the 90s, and the 2000s, most recently in 2013. And it's just like really bad, right? I mean, look at these numbers. These are really bad. This is not happy at all. Right? And the more negative examples people found of this, people started to question, well, maybe this is just beyond students' abilities, right? Maybe this is not, maybe we have completely misestimated what students are capable of doing, and CS1 should be much, 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 much less than what it's expecting students to do now. Right? So you start off with this very optimistic idea. What Elliott Soloway wanted to understand is, given this problem, how do students plan out a solution to it? We go from that very aspirational view in 1986 to 20 years later, 30 years later, we're like, maybe CS1 has to be completely broken down because nobody can program, and programming is too hard for anybody to do. Right? It's pretty dismal, pretty sad story. Okay. Now, this also helps to understand, I mean, we're all experienced programmers here, so it's not that hard to solve this problem, right? Which is why we hand out this problem to our students. Why is this difficult? Well, because there's actually a lot of pieces to this problem, right? If you break it down, there are roughly like 6 different steps, parts to this problem. And any one of these is a place where you can make a mistake, right? So in 2014, my colleague, Kathy Fizzler, did a study on this problem again. And there were several parts to her study. One of it was she tried to assess the structure of solutions that previous students had used. It's a little hard, you know, sort of trying to reconstruct from papers that don't really describe things too well. But roughly speaking, what she found was, historically, about 70% of solutions had a single loop through all the data, and about 30% of students didn't even have an identifiable plan. Okay. Now, if you go back to the 80s, this is not actually surprising, Because when the problem was originally handed out, it was in the context of languages like Pascal, where like a linked list was a pretty big deal, right? Like, I mean, it was like sometimes a CS2 topic. You had to teach people pointers and all these other things. There were no arbitrary linked data structures. The problem doesn't put a bound on the length, right? Anybody who learned CS in the 80s remembers all of your problems always told you how many data there were going to be. Why? Because you could program with arrays. This problem doesn't give you a bound. So basically, and you also had keyboard input output. So if you have keyboard input output and no data structure, the only thing you can do is to try to process the whole thing in a single loop. You don't have a choice in the matter, really. Okay. So what Kathy did was organize a group of institutions to do this study. These were different schools. They were like, institutions across different levels. There were high schools and college. The key thing is they were all using this book, How to Design Programs. And they were using a few different programming languages, Racket, OCaml, and Pirate. And they were all functional programming, okay? And what she found was a very, very, very different outcome, okay? In particular, she found that students in across these courses tended to use solutions that had 3 different structures. Some of them had the single loop, just like before, right? Where basically you keep looping till you find a sentinel. You keep accumulating a count and a sum. When you're done with the loop, or when you run out of sentinel or the array or list, you come to the end and you compute the average. There was a second structure called clean multiple, where you loop until you find the sentinel to the counting. You also loop until the sentinel to the sum, and now you have the sum and the count, and you compute the average. And the third one is quite different from these. Third one is basically saying, look, all you're trying to do is to compute the average of a list of numbers, okay? The problem is you've been given a noisy list of numbers. Your numbers have 2 kinds of noise. They have a sentinel value, after which you want to ignore everything, and they have all these garbage negative values. So really what you want to do is you want to transform it, cleanse it into a clean, simple list of numbers. Once you do that, we know how to compute the average of a list of numbers. That's pretty easy, right? So that's what she called the clean first solution. Okay, so now here's what I want you to do. I want you to type into the chat, and you can just hit enter right away, which structure you had. Were you a single loop, a clean multiple, or a clean first? Go for it. Interesting. So we have some diversity of solutions here. Some of you are single loop people, some of you are clean first people. Clean first, my fam. Good. Okay. So, and single loop, more clean first. Okay, interesting. No clean multiples in this, but you're pretty evenly split between these 2. That's very interesting. So here's what Kathy found, right? So when she did the study across these institutions, she found a very different demographic. It looked like this, where the orange bar is clean first and the gray bar is clean multiple. And most of the students were doing the orange and the gray bars, okay? And there's actually a very small number of single loop students. And in particular, the error rate went very, very low. In particular, the students who had the clean first and clean multiple had extremely low rates of errors. And to some extent, what was really happening was students were retrieving knowledge they had about built-in functions and higher order functions, right? So when you look at the clean first solution, for example, what you're looking at is saying, well, I mean, I need to compute the average. How do you compute the average? Well, I need to compute the length. I know that's a built-in function. I need to compute the sum. Well, that's just a fold over the list. But how do I clean the loop? Well, that's just a filter. I know how to do filter. I know how to do, so now you get this nice, clean compositional structure, and you get a plan that you can formulate and you can write down a solution. Okay, so we have since done a lot more research on this. We've come up with a bunch more functions like this we're trying to really capture the essence of sort of modern data science like tasks, where you have these tasks that are like, cleaning data, what we call parsing. I don't mean parsing in sort of the traditional compiler sense like byte stream, but parsing is you want your data, I think of parsing very generally. You want your data to have a particular shape, you're given data in a different shape. You just have to translate shapes, right? You might have wanted a tree shape thing and you got a list, or you wanted a list of lists, you got a single list translated. And once you translate it in the shape that you'd like, it's a lot easier to solve the problem, right? So we've built up a collection of these problems, and I'll get back to this in the third part of the talk. But the critical thing is all of the work up till now has largely been you look at the solutions that students wrote, and you try to determine what plan they were trying to use, right? It's sort of this heroic effort to reconstruct a plan, okay? Which I know might appeal a lot to the ICPC crowd, but let me point out a problem here. If you have the wrong plan structure initially, it's going to be very, very hard to solve this problem, okay? And in general problems, if you have the wrong plan structure, because what you have to do is you have to back out of one structure and start a new structure, okay? And I like to joke that students, especially intro programming students, are like 3D printers. They work purely by additive manufacturing, right? So they have some amount of code. They're only going to keep adding more code, right? If code got them to a position where things don't quite work, clearly the solution to that is more code, not deleting, certainly not throwing out everything and starting again, right? And it's easy to understand why. They're anxious, they're, deadlines coming up, they've spent all this time, sunk costs, et cetera, lots of good cognitive reasons why they don't want to do that. So the thing to do then is to recognize that and to try to avoid putting them in that situation in the first place. So what we've been doing lately is asking, what if we do in the forward direction? What if we have students write plans before they start programming? And Kathy and I have tried different approaches. The thing that I found particularly successful lately is we start with Snap, which is a block-based programming language. It's a descent of Scratch, if you've heard of Scratch. And the key thing with Snap, I suppose we could have used Scratch for this as well. Snap lets you configure things much more. The thing with Snap is, with any of these kinds of block languages, is in the blocks you can write text, okay? So these are actually 3 different plans that students of mine wrote in the fall semester for the same problem. And you can see the first student basically said, it's a filter on the outside, and I'm just going to write some text on the inside. The second student said it's a filter on the outside and it's an AND map on the inside. I want to give you short descriptions of what happens and what the arguments for the AND map are. And third student says the filter on the outside and AND map on the inside. I'm going to give you long, complicated descriptions in a lot of detail. Okay, and you don't have to read these. All 3 of these are actually correct. They're all conveying the right idea. But the thing is, this is this nice mix of like structure on the outside and prose kind of where you bottom out, right? You're either uncomfortable, you're not sure, or it's not important. You're getting bogged down in programming details. It's not relevant to the planning details. This structure seems to work really nicely. And we've been doing research analyzing the effectiveness of this. And so far, we're getting pretty good results. Okay. So now again, end of the second part, I want to tell you about the relevance to ICPC. Here's a problem we have. We would love to get clustering techniques that group programs by plans. We have sent our data to several people who claim they have good clustering techniques, and it's been pretty dismal. Nobody has come back to us with like particularly good solutions. So anybody on ICPC who thinks you have really good program clustering techniques that can take, for example, the problem that I sent you, yeah, right, I showed you the rainfall problem, and can say, for example, give me the clean first, clean multiple, and single loop as clusters, would be fantastic. Now, one thing to note is our programs are not in Java, they're not in Python, they're in like Racket and Pirate and languages like that. And so maybe you don't have clustering techniques that work for that. But anyway, if there's somebody in this listening who says, I have awesome clustering techniques, I think I can do something, we have a data set and we'd love to sit down with you and validate your technique. And if it works, we can give you, we'd be happy to serve as evidence that you have a good technique. So consider it a challenge to the community. Okay. But I also want to point out, we're now starting a new kind of programming, right? Which is these plans as programs. They're intentionally not executable. There's prose in there. They're this hybrid of code and prose. And these are things we want to evaluate and pass judgment on and give feedback to students to say, you're on the right track. Go off and start coding. You're not on the right track. I want to give you feedback, right? So this is a different kind of program comprehension where the programs are these hybrid programs. And again, if you're an educator, then what's the thing for you? Well, we have a collection of problems. Given this sordid history of plan composition, it's something you might want to think about, especially if you want to prepare students for data science and so forth. And I'd like we have problems we can share with you. I'd also like you to consider doing this explicit planning. We're happy to share some of our infrastructure with you and talk to you about that. Okay, that's the end of the second part of the talk. Now I'm going to move on to the third part, which is performance comprehension. Okay. So let me go back to the slide that I showed you before, right? And we said students with a clear structure make few errors, right? And in particular, the successful ones, right? Those 2 bars have an interesting characteristic. The interesting characteristic is they make multiple traversals over the data, right? And this is important because there's a question of what impacts students' plan structures. And we did a study that tries to understand what kinds of variables students take into account when making plan structures. Turns out a major variable is perceived performance. What is particularly interesting is we got a lot of this from a course, where an introductory class for students with no prior CS, where the professor had supposedly told them very explicitly to not think about performance. Make of that what you will. So why are they thinking about it? I don't know. Maybe it's the TAs, maybe the very fact that the professor told them not to think about it. I don't know. It's an interesting question. Okay. Now, we then did this sort of multi-institutional, multinational study, and we had some collection of students who were working imperatively and some students who were working functionally. There were a lot of findings from that, but the high level finding relevant to this part over here is, roughly speaking, the single loop solutions came from imperative programmers, the multiple traversals came from functional programmers. Okay. I don't know how the people in this chat will identify themselves. It doesn't matter, but I'm saying like that's what we found out of this study. Okay. So now I'm going to give you one more sample problem. Okay. So last homework for the talk. Don't worry. Okay. So here's the task. I want you to check for palindromes. We all know checking for palindromes, right? I've done it like 100 times. But there are two twists. I want you to ignore capitalization and ignore punctuation. So ignore capitalization means upper and lowercase letters are the same from the point of view of being a palindrome. Ignore punctuation means pretend it just doesn't exist, like you just skip over it. Okay? Go. Think about it for about 30 seconds. Think about how you do it. Okay, so I suspect by now all of you have like completely implemented it even. So let me tell you, when I look at a problem like this, right, what it triggers for me is when somebody says ignore capitalization, I think of this as sort of a mapping or transforming, right, normalizing the data, right? And when I see ignore punctuation, I mean, it's the same word ignore, but it means a different ignore here, which is I think of it as a filter, right? Cleanse the data, right? And if you think about the kinds of advice people are now giving data science programmers like Hadley Wickham's books and talks, he's telling data science people who have no prior CS and are never going to be computer scientists, these are the ways you want to think about approaching data processing, right, in terms of these higher order functions. So this is how I think about it. What is surprising to me now, of course, and by the way, notice that if you structure things this way, it actually opens up many more solution strategies, right? If you think about this sort of imperatively walking pointers, walking from back to front, you kind of have to duplicate the logic of jumping over the punctuation and duplicate the logic of ignoring capitalization. But if you think of this as first a cleansing, normalizing step, now you have other solutions, like you can just reverse and compare the strings and so on, right? There are more solution strategies present themselves. So what was very interesting to us on the study was that even the imperative programmers did multiple traversals. Now, one possibility is it's just the problem is hard enough that they gave up and they said it's okay to take a performance hit, something like that. When you start digging into the code, you realize what's going on is they're using library functions like replace all, right? So there's this sort of schema retrieval, and they're like, this reminds me of a filter or a map, right? It reminds them of a replace all, and that the replace all contains additional traversals. So that's where the additional traversals are coming from. Okay, so in a way, this is good news, right? Like these students are not so fixed in their mindset. They're actually open-minded. They're willing to use multiple traversals if it makes sense for a problem. Well, there's a catch. When we asked them to rank solutions, more than half of them ranked efficiency as the primary criterion. What was actually going on is they didn't realize replace all was actually doing a traversal. Okay. And based on this and some other work I've done, I've started to realize that, like behavioral economists talk about how people have sort of this sort of non-rational, not the Homo economicus model of accounting in their head, right? I think something similar is going on here. Students have all sorts of weird models, cost models of programs. And in particular, a library call is a single line of code, and single lines of code are roughly speaking atomic. And so library calls just don't count. They don't count towards your cost budget from what I can tell. Okay, so there's some strange things going on. And so they're willing to use these more rich expressive solutions as long as they don't see it. It's like there's a dispensation and they don't have to see the cost, then it's okay. It's hidden behind the scenes. we've more recently started to do some additional research where we ask students to rank programs that are actually equi-performant, in some case literally equivalent, like one is just the desugaring of the other program. So from the compiler's point of view, they're exactly the same program. Okay, and students see all sorts of differences between these that simply do not exist. We've tried using techniques from cognitive psychology that are in other domains, like in climate change and domains like that, used to break people of like their really strong mental models. And those are not as effective in this universe. So there's a lot more that we need to do to understand what's really going on here. Again, to wrap this up, bring this back to ICPC, the programs we see, the important thing to understand is that the consequence of these very complex, not necessarily rational, certainly not accurate, and oftentimes not even consistent mental models of program performance. And surely that should factor in somewhere in the way you think about program comprehension. Okay. And now the advice to educators is, guess what? Your students have complex, irrational, inaccurate, inconsistent mental models of program performance, and that is affecting the way they program in all sorts of subtle ways that you may not have realized. Okay, so those are the three parts that I talked about. I think of program comprehension as sort of coming in from the back, right? The program is already there, we're trying to comprehend it. I want to spend a minute talking about the other direction, which is, what comes before PC. Well, it's the next letter, but it's PD, it's program design, right? And I want to step back and think about the word design for a moment, because there are many design traditions and there are many communities that do design. Right? If you are an architect, for example, you don't, even Frank Lloyd Wright, I picked this example on purpose because he was not actually the best of architects from a structural engineering perspective. But even Frank Lloyd Wright didn't just go off and start putting concrete and stones together, right? You start off with like floor plans, you create like, structural diagrams, you do measurements, you do calculations, you do projections, etc. And you do all these different things before you go off and start building a house. Right? If you are an electrical engineer, right? So this is actually the famous first Apple, the single button Apple mouse, right? And these are actually pictures from the patent for that mouse. And, if you think about an engineer, like an electrical engineer, they don't just go off and start like, doing injection molded plastic first. They start by viewing this thing from several different perspectives. They build out schematics, right? There are circuit diagrams, there are timing diagrams, there are all these different representations they use to understand this thing. And the key thing is, in general, design is a multi-stage process. There are multiple different representations we use, and each of these representations gives us a different viewpoint. Each one tells a bit of a lie. It highlights one thing and obscures something else, right? This is how we do design in general. This perspective is almost completely missing in programming education for novices. There's an empty buffer, you go ahead and start typing. That's it, right? When you're done typing, you click submit, you upload it to a server, and you hope for the best. I think this is very disappointing. It's unsurprising that students struggle to solve problems. Part of the difficulty is our expert blind spots, right? Anybody who's at this conference is probably a very, very good programmer. So you don't appreciate the difficulties that your students have. Right? The problems I showed you, you could solve in your sleep, but your students can't, because developmentally that's still difficult for them, right? So they struggle, and then we struggle to reconstruct what intent they had, what path they took, et cetera, et cetera. Maybe if you could bring more of this idea of design into program design, that would be really good, right? I've given you some concrete examples in this talk. For example, the idea of writing some examples first, the idea of writing some plans. There are lots of other things. Like, in fact, I mentioned the book, How to Design Programs, right? We take the design tradition seriously. There are lots of different representations we want students to use. Now, they have to be lightweight, right? It doesn't make sense to throw UML at a beginning student. UML is it's a weapon for an experienced programmer. It doesn't make sense for a beginner. But what are the equivalent notations we can use to help for students to get some feedback, to try to understand what they're doing? Okay. There's papers and all of this, interesting, unsurprising. That's my talk. What I wanted to talk to you about mainly was problem comprehension, plan comprehension, and performance comprehension. I claim that all of these have consequences for program comprehension as well, especially in a novice world where things are much more weird and confusing than you might have necessarily assumed. Okay, that's the end of my talk. I wanted to have plenty of time left over for Q&A, and so the rest of the time is all yours. Fire away.
Thank you so much, Shriram. That
Thank
talk
you.
was awesome.
Thank you. Thank you.
As a proof, I forgot to tweet about it because I was so into your talk and taking notes. So the floor is open for questions while people are typing
discussions,
in.
comments, anything. It doesn't have to be a question. Any thoughts you have, I welcome.
Sounds good. Yeah. So I will start while people are formulating questions. I was wondering, so, most of the examples that you showed us are about, introductory CS courses. I was wondering, to what extent, or if you have done any work on that, to what extent do you feel like those problems and solutions that you have currently are applying for also, courses that are more high level? So, for example,
that's a really good
300.
question. Yeah, Venera, that's a really good question. And it's actually, to my mind, it's frankly, one of the major criticisms that I have of the computing education research community is it's obsessed with K-12 and introductory CS. And I think, partly it's an artifact of who publishes, right? A lot of the people who publish are people who teach intro classes, and that's the audience that they have. Right? There's very little there's some work on informal education, boot camps and things like that. But it's kind of surprising. We have almost everything but upper level collegiate computer science, right? There's very little on that in the research side. I've actually been doing some research. Of course, what we do is we end up studying the courses that we teach because that's what we have easiest access to. I've been doing more and more research trying to understand how to teach programming language, not teach programming, that's separate, but teach programming languages as a discipline. And we've made a fair bit of progress. Part of what we're finding is some of the sort of long cherished techniques in the community maybe don't work so well. And we're starting to first sort of chip away at the edifice before we can build it back up. But I think a lot of the things that I'm talking about here are primarily oriented towards beginners. And that's sort of on purpose, so as you said in the introduction, we also have this project called Bootstrap, which is one of the largest computing outreach programs in the US. And so there we're working with students as young as like 10 to 12 years old, right? Middle schoolers. And we do a lot of work there actually in what we call integrated computer science. We don't teach CS classes. We work with teachers in math and physics and social studies and so on to inject computer science into their class. Now that's a very tricky thing because the average math teacher doesn't wake up in the morning saying, today I want to teach, I've always wanted to teach computer science finally, right? They want to teach math. They love math. That's what they're excited about. And every country has its own peculiarities. As some of you know, in the US, like English and math are high stakes subjects. And so they don't want you doing random, come and let's have fun in the math class. That isn't going to work. Right? They need to know that any computing you inject in the class is going to actually change something, improve the math outcomes. That's the critical thing, right? So we work very closely on designing pedagogic interventions that are going to improve learning in those subjects and secondarily teach some computing. So I'm interested in that whole, I'm definitely interested in sort of the, stuff all the way to the graduate level when it comes to like computer security and privacy, right? That's another topic where there's a lot of interesting unanswered and even unasked questions. But when it comes to programming, I'm really interested in sort of everything from the 6th to 8th grade all the way to introductory, because I feel like dealing with the most vulnerable population is important if we're going to achieve, if we're going to get computing to everybody and we're going to improve diversity in the subject and so on. They're more vulnerable than, upper level, say, software engineering classes. But we know almost nothing about how to do these courses. We know almost nothing. It's shocking how little we know, especially from a sort of scientific measured perspective. And I don't just mean like quantitative, right? Qualitative. I love qualitative methods too. Any sort of rigorous methods, we have almost nothing. And so people who are listening, if you find any of this interesting, please by all means get involved or talk to people like me. Happy to talk to you about how to get involved and so on. There's some questions in the chat. Do you mind if I start going? And
yeah, go ahead. Yes,
okay.
Go ahead.
Matthew Nassif says, question about test-first approach you described. Do students realize the benefits of writing good unit tests when they have a lot of deadlines, want to finish the task quickly? In my experience, many or most will do the minimum and something isn't graded. That's a great question. So Matthew, one thing I would point out, the sort of obvious thing that you, of course, realize is just make it graded, right? If students won't do testing because it's not graded, make it part of the grade. So in my course, there's a very important thing is like, you have to be responsible for the software you produce. Testing your software is not my responsibility, it's your responsibility. It's sort of sense I say like in the US, you're supposedly, innocent until proven guilty. In my class, you're guilty until proven innocent, right? You have to convince me that you've tested your program enough to like pass muster. But in the exemplar approach, we do more than that, right? there's careful UI design, there's the nudging factor, and so on. And the fact that students realize, so one of our papers literally, in fact, here's the title, right? Will students write tests early without coercion, which is exactly your question. And the answer is, through a combination of factors, it appears the answer is yes, they will, but it requires them to get real curricular value out of it. The user interface has to be comfortable and copacetic. It has to not tax them too much. And you have to put some little nudges that force them to actually do this early. And if you do, it appears, at least on our limited experimental analysis, yes, they will. Okay. So I hope that answers your question. You can either verbally say yes or respond in the chat if that answers your question. Okay. Okay, next is Sonia's question. Learning by example is also how little kids, yes, learn about how the world is. So it seems like a very natural way to learn. Do you think learn more from how little kids learn about the world and apply some of those things to how students learn programming? That's a really, really great question. I think yes, and a little bit, but with a guard on it. Okay, so yes, in the sense that yes, I think there's a lot of insight there about learning broadly that has not yet been applied to learning, say, computer programming. The little asterisk I put on it is what we typically learn about the world is concrete artifacts. Programming is an abstract activity. Right? There's all sorts of levels of abstraction, right? There's the world out there. We have to represent the world in a model. We're then working with that model. And furthermore, we're not solving one instance of the problem with the model. We're writing a program that solves all instances of an abstract. So we have a thing that does all instances, which is an abstract thing, of a model, which is an abstract thing. So it's like abstract squared. Right? So for that reason, we have to be a little careful about how effectively we can bring those ideas in. Okay. Now, that said, to be honest, my actual research agenda is how do people learn abstraction, especially in computer science? That is my sort of life goal, is to figure out the answer to that question. And a lot of it really has to do with examples, right? Because how people learn is, most people generalize from concrete examples. The tricky thing when you do that is you have to give them the right examples, otherwise they'll learn the wrong generalizations. You won't even realize it, and you'll find out much later that they picked up completely the wrong thing. Right. So I think a good example of that is the median function, right? If you didn't force them to confront that the median of 132 is 2 and not 3, they'll happily say 132 is 3, and then they'll go off and implement the thing that takes the middle of the list and returns the middle of the list, and they'll be completely oblivious, right? Because people will generalize poorly in general. Right? So figuring out how we produce diverse examples that illustrate this, there's actually some very interesting cognitive science here about the theory of contrasting cases and the theory of concreteness fading, both of which we start to do. So actually, this goes back a little bit to Venera's question. One upper level subject we have done a lot of research in is how to teach formal methods, and in particular, how to introduce students to formal methods from informal methods. Like, how do we start from testing? We go from testing to property-based testing to formal specification in this progression, because we go step by step from the concrete to the abstract. And then how do we generate the right kinds of examples so that people pick up the right things? That is very much an active area that we've been working on. And in that sense, I think, Sonia, we're definitely recapitulating some of these ideas as much as we can, but taking a broader cognitive approach that's not just students, but you're basically what you said on that track. Okay, hope that makes sense. Okay, Lingxiao Jiang says, thanks for the interesting talk, thank you. Is a plan like choosing the right data structure plus algorithm? My impression about traditional programming education to focus on data structures, how is it not enough to differ from plan or program design perspective? That's a great question. So the problem is, the word algorithm in your question is doing a lot of work. Okay, so you say that traditional programming education focuses on data structures plus algorithms. I would argue that most programming education gives students little to no guidance on how to generate that algorithm. Okay, so students face, a student is confronted in general with what I call the blank page problem. Right, the blank page problem is they have a page that has a problem statement on it. They have a blank screen that's either a paper or an editor, and somehow they have to magically fill up this blank screen with magical incantations that are going to exactly solve the problem that they are given. The question is, what guidance do we have for helping them to, we're basically asking them to go from 0 to 100 with nothing. Okay, what guidance do we have to scaffold that process so they can make step-by-step progress? Okay, I mean, I've read the Data Structures Plus Algorithms book. Basically, the traditional advice is follow top-down design. Well, what is top and what is down, and how does that help me? Well, break it down. How do I break it down? The problem is a lot of these traditional approaches assume that you already know how to do it because the people who were teaching it already did know how to do it, right? We're trying to say, look, let's assume that our audience doesn't already know how to do top-down design. If they did, why would they be in an introductory programming class, right? That's not a skill people are born with. That's not a skill people natively have. So what we're trying to do is to take that algorithm part and break it down into steps where students can interactively try to progressively refine their solutions and get feedback along the way to figure out whether they're on the right path or not. Okay. So, and that requires these multiple different perspectives, these multiple different representations, multiple different kinds of feedback, but also break it down into small stages so they can feel a sense of progress rather than you have to solve the whole thing before you get any feedback, right? That's what typically happens. You have to write the whole program. You might have an auto grader, but you have to write the whole program and submit it to the auto grader before you can get any feedback. Okay. Yes, and Vinara points out 10% on testing. Yes, great. Matthew, yeah, I think you could find it off my webpage, but if you don't, you're welcome to drop me email. I'll show you I'll show you the title of the paper. Oops, sorry. There's the title. Will students write tests early without coercion? That was the paper you asked for. Ling Xiao, okay, thank you. Any other questions? I know at some point we're also going to start running out of time, so I want to be respectful of your time here.
Yeah, I think we have 2 more minutes. So if someone has a quick question,
I will try my best to give you a quick answer. It's really my fault. I know what you're saying here.
Go, Sonia.
I have a question. I figured I'll unmute myself to make it quick. So it's really interesting to see, how you are saying that students have this, they put performance first and how they think about that without knowing exactly where this comes from. Well, I realized that that's also how I'm thinking when I'm writing programs, and I don't know why, and I don't know where it comes from.
Yeah.
And I just have this ingrained in my head that I would never think of traversing something twice if I can do it in one pass. And I feel like some of this is coming from high school teacher of programming who was always trying to get us to write as performant programs, as performant as possible. So I'm wondering if you think this comes from earlier education.
That's a great question, and I must say I really appreciate your honesty in describing yourself this way. Here is a very interesting thing that I've noticed in my class. So I get students, I actually teach an accelerated introductory class, which is typically students who've had a lot of high school CS. And so we want to get them out of the population and not disrupt the other classes. So we go, we do the whole first year and a semester. Okay. And so these are students who've all been taught the mantra of performance, right? And in fact, we've been trying to study where do they get these from. A lot of them get it from high school. They get it from message boards like Reddit. They get it from their peers, occasionally from their parents, right? So there's this thing that's been drummed into them. Now, what I've noticed is, so in my class, I talk, we discuss the plan composition problem. We talk about the multiple traversal. One of the things I point out is, depending on your language and compiler, if you were to write a collection of higher order functions composed, right, like maps and filters composed, there are optimizations like deforestation that will basically combine these loops, right? It's called loop fusion or deforestation. It'll take these multiple loops and combine all the bodies and turn it into a single loop. So the thing that you were painfully doing by hand, you're going to get for free anyway. The compiler is going to do it. You get your nice expressive program, but you get the same performance. Okay. And then I tell them, but here's the thing. That's not a thing that the pirate compiler, which we're using here, does not actually do that. Okay, so I want to be completely clear, complete honesty. The compiler you're using does not do that. I know because I know the internals of the compiler doesn't do it. Turns out this actually changes a bunch of students' minds. Okay, they start liberating themselves, even though they know they're not getting it. And I really think it is almost like a moral sense that they have. They have this moral feeling like I've done something sinful or unclean if I write these multiple traversals. As long as there exists a mythical compiler somewhere that will do it, even though it's not the one I'm writing, it could exist, right? Good enough. I'm now liberated to go off and program in that style, right? So the thing is, I think it's really complicated. We are actually studying this question right now. Where are students getting these conceptions from? What is the naive cost model? And you know, I think also the interactions with, sorry, can I have one more minute? Or do you want me to shut off? Okay, I think our interactions with everyday computing are also going to end up having a significant impact, right? Let me tell you this. I am very, very surprised that when a professor tries to teach, you know, like search takes logarithmic time, okay? I am very surprised that students say, no, that's not true. Search always takes constant time, proof Google or Bing, whichever you prefer, right? Or Neva or whatever, right? DuckDuckGo. I mean, like the internet, you tell me the internet keeps growing, and yet it always returns a search in constant time. So how can search be logarithmic time? That just doesn't, I mean, like the fact that students don't question that actually to me is a little disturbing, because it suggests that they're not like connecting up these different pieces, right? There's search over here and search over there, and those are two completely unrelated things, right? Somehow the search that's happening in class is unrelated to search that's happening on the web. Why aren't they questioning it, right? Like, what's going on? What is the disconnect? I mean, in education, this is called transfer, right? You see something in one domain, you can apply it in another domain. There's a whole literature on like near transfer versus far transfer, et cetera, et cetera. This is a transfer question, right? Are we not telling them that it's the same, so it's a related search? If we are, they should be questioning us. If we're not telling them, are they not making the connection? What's going on, right? I think we have, so more and more, I mean, like I'm required by my department's curriculum to do Big O in that semester. I am more and more like, I want to do something related. I think we need a science of like naive cost modeling. And it's a naive cost modeling that takes into account the cognitive factors coming in and tries to reconstruct those in new ways. Because it's clear that all the Big O stuff we're doing, it is not transferring to anything else, right? There's Big O brain over here. There's cost model brain over here. They're programming the cost model brain, and the Big O brain barely affects it. So I think we need to rethink all of this. So I think we have no time for any more questions, right? Is that right?